All right, good morning, everybody. Since we missed school yesterday, what we're going to try to do is record a nice video of what the lab you would have done would have been, so that you can have some idea what happens when you look at this data. So when you're writing it up and looking at the data, you have some idea what the heck we're talking about. Hopefully it's helpful. It's also the first time we're going to try to do one of these Google Glass lab casts or iCast, or we got to come up with a clever name for it. It's still in beta. So the whole idea of this, we have our wonderful cart, we have our ramp, and the idea is that the cart goes down the ramp. Shocking, I know. And then it goes up the ramp because we didn't set this up perfectly. Turns out this is tricky to do as a one-person operation. That's why we do labs in groups. All right. When we've done this before, we looked at it from like a kinematics perspective. We talked about position, velocity, acceleration a little bit, forces maybe. This time, what we're going to talk about is energy. When we start, the cart is elevated, showing here, kind of upside down actually, and backwards. Right. Also transparent and not really easy to see. Cart starts high up, which means it starts with what kind of energy? Take a second, pause the video if you need to. Exactly, right. Gravitational potential energy. When we let the cart go down the ramp, cart starts moving, meaning it's all of that gravitational potential energy has been turned into, this actually is kind of convenient now that I think about it. Anyway, all that gravitational potential energy has been turned into, take a second, pause if you need it. Exactly, kinetic energy, motion. So, theory should be, first law of thermodynamics says, is that energy is conserved. It can neither be created nor destroyed. So, if we start with kinetic, or start with potential, end with kinetic, we should start with the same, we should have the same amount of potential energy as we have kinetic energy, unless something weird happens in the middle. So that's what we want to try to investigate a little bit. So the idea is we're going to use our handy-dandy probeware to figure out the position and velocity of this cart and see how this energy stacks up as we go down the ramp. First things first, we need to make sure this thing is zeroed properly. So if it's not, that's just really going to be annoying. So we're going to set up our sensors, motion detector. We are going to zero it right here at the top of the ramp. We're going to make sure that the cart is basically at 0. Cart is basically at 0. So this lets us make sure that the position that the sensor reads is the position on the ramp for the cart, which is really, really useful. Zeroed. All right. So, idea being, we're going to collect the data, hitting collect. We're going to let the cart go down the ramp. We'll get our position data, we'll get our velocity data, and then we will go from there. So, here we go. Hitting collect, letting it go. Nice. Now we stop it before it goes back up the ramp. That's actually growing on me as a matter of convenience, not inconvenience. All right, so let's take a good look at this data. We've got a whole bunch of nothing, where it's at the top of the ramp just sitting there. And then we have this interesting bit where it's actually going down the ramp. So, let us get rid of the nothing. Here is the bit in which we have interest. Actually, I guess let's try to start from velocity appears to be starting from. And then down here, it's hitting the book, so we're not really interested in that. So we'll stop it right around here before it starts slowing down. The collision with the book, complicated. We don't want to worry about that right now. So, what we're looking at then, I'm kind of recording something.
Oh, never mind.
Ignore Ms. Yam. Not ignore her, but just at the moment, ignore her. Do you think I was talking to myself? Anyway. Looking at the data we want to go from time mark 47 to time mark 77. So, we'll take out the first 46 points. I'm going to highlight them all up. And then edit, strike through data cells, which takes them off of our graph, very conveniently for us. And then we said we wanted to go through, what, 76? We'll see here. Yes. And so we'll take out the last couple of points, edit, strike through data cells. So now we only have this. We're running from, let's see here. Oh, help if this would play nice. 2.35 seconds to 3.8 seconds. So we'll reset the scale of this. Manual, 2.35, 3.8, done. let's get these things scaled. We'll auto-scale them on both axes. Nice. So you can see this is not perfect. I don't know why the cart, for example, slows down right here. That's a little weird. But it's going to be, it's reasonable, something to work from. All right. So now that we've got all this, we need to think about. So we got the position of the cart tracked for us. We've got the velocity of the cart. But if we want to talk about gravitational potential energy and kinetic energy, what we really need to talk about is height of the cart and position and speed of the cart. So if we look, we've got a solid, almost 30 data points here. It takes a long time to measure 30 heights. It's kind of annoying and tedious. I should know because I tried doing it. So what we're going to do instead is measure some of them. So we're going to put in a new column, new manual column. We're going to call it height. We're going to give it an abbreviation of little h. It's measured in meters. That's done. And so we're going to measure a couple of these heights. And so we can figure out which ones to measure by the position of the cart. So we'll measure, the first one, not sure what's up with that whole negative, well, I guess it's negative 2 millimeters, so whatever, we can call it 0. So I'm going to come over here, and let's measure some heights. And then we are going to try to put them into our spreadsheet and see what happens. The problem is I only have a clear ruler, which also has an offset. So there's a lot of complicated stuff going on here. I also don't know if we can really see this. So anyway, all right. I'm sure I'm screwing with the focus on this thing. All right, the offset I know from before is 7.5 millimeters, so 0.75 centimeters. Where was my other ruler? The other ruler, inconveniently, has a rounded edge at the bit where the centimeter begins. So I'd have to either subtract things or go backwards, or there's really no good way out of this. It's a little frustrating. All right, so anyway, here's 0. Here is this. This would appear to be, oh god. This is where glass gets in the way a little bit. All right, so this looks like 8.4 centimeters plus 0.75, so 9.15 centimeters, so 0.0915 meters. All right, now let's skip down 5 spots or so. So 1, 2, 3, 4, 5. So we want to go to when the cart is at 6.5 centimeters. So we'll slide the cart down the ramp, and we'll measure the height again. Thrilling work, I know, but necessary. And again, easier when you have more than one person doing this. You want to make sure that we have this, in fact, in centimeters. All right, so now we're looking at, well, it looks like, I get this thing level, 8.1, which goes to 8.85, so 0.0885. Skip down a couple more, 1, 2, 3, 4, 5, 16.9 centimeters. This is where actually having the book as a brace turns out to be quite useful. All right, 16.9. Let's see where we are. All right, this puts us at 7.6. 7.6 plus 0.75, 8.35. You may want to double check these numbers when you do them yourself. Well, not that, I mean, you guys won't be doing them yourselves, but you want to write down the things that I'm saying out loud and make sure I'm not doing my math wrong. 1, 2, 3, 4, 5. 29.3. All right. 29.3. Also, if you can actually read the numbers, you may want to double check against that. This looks like 7.3 to me. So 7.3, 0.75, 8.05, so 0.0805. So again, centimeters to meters. 1, 2, 3, 4, 5. 43.9. Moving on down now. Why are these more spread out even though I'm going the same amount of time between each one? You can think about it for a bit. But it's tied to what the cart is doing as it goes down the ramp. All right, we know the cart is speeding up, so that means that if it's going faster, in the same amount of time, it will cover more distance. So let's see, this looks like 6.7. So 6.7 plus 0.75, 0.0745. 1, 2, 3, 4, 5. 1, 2, 3, 4. Whoops. No, well. 1, 2, 3, 4, 5. 60.4. Let's see, right around here. So now when I'm doing this, I'm measuring to the bottom of the cart, which is, again, just an idea. It's all about this whole thing of a reference level. As long as I measure to the same part from the same part, I should get the right change in height. This appears to be 5.9, thereabouts. Yeah, I'd say so. 5.9, so 6.55? 6.65. 0.65. Yeah, 5.97.75, right. And then our last one, 74.8. Doesn't really seem like it should be our last one. Not really sure what's up. I guess I took out a couple points and it must be doing some weird stuff in terms of extrapolating. Anyway. Oh, we got a few more minutes. Alright, this takes us down to 5.4. Yeah, I'd say 5.4 or 5.3. Yeah, it looks like more like 5.4 to me. So 5.4 is 615.0615. Alright, so now we got all these heights. So we have speed, we have height. We know that kinetic energy looks like 1/2 mv squared. We know that gravitational potential energy looks like mgh. Both of these involve, oh, that's where the cart went. Both of these involve mass. So we need to know the mass of our cart. So, check, make sure this thing is zeroed still, which I mean it should be. I don't think the temperature is that extreme fluctuating in here. Not quite zeroed. Someday I'll get a big digital balance, but right now these things blow out the ones that we have. Just by a little bit. Oh, still a little too big. Let's try it again. I gotta hurry or YouTube's not gonna like this video. Close enough. Alright. I happen to cheat and know the mass of this thing basically, so I'm gonna go right to it. Oh, not quite. This one's a little heavy. I'm probably putting away the snacks over winter break. Alright, the mass looks to be about a little further than that, maybe. 501.7? Yeah. 501.7 grams. Which is, again, a good thing to write down somewhere. So, 501.7 grams is 0.5017 kilograms. So now, we can calculate some energies. So this is the data that you will get. So I'm going to save this as cart energy class data. This is what I'm going to give you guys. After this, you got to carry out the rest yourself. So we're going to add a new calculated column. We're going to call this potential energy. Call it PE. It's measured in joules. And we need to say what it is. So it's going to be the mass, which we know is 0.5017, times gravity, which we know is 10 meters per second squared, times the height. So we're going to go multiply it by the height. We go from variables, we select height. So we get for these 6 positions, 1, 2, 3, 4, 5, 6, 7 positions even, I can count. We get a potential energy. And so now, I'm going to add another calculated column. Call this the kinetic energy. Call it KE for short. Units of joules. And we note this is half times the mass times the velocity squared. So we'll go times the velocity times the velocity. This gets a little finicky if you try to do it other things. And so one more thing we want to talk about is the total energy, which we can just call E, still measured in joules. And the total energy should be the potential energy plus the kinetic energy. And so what we want to talk about now, we can make a graph. And this graph should be total energy versus time. And it should be constant. It looks like it's kind of all over the place. So let's add a couple of things to here and see what it looks like. Let's put the potential and the kinetic on it as well. And we will auto scale. So now it looks a little better, right? Here's the total energy. Here is the potential energy. Here is the kinetic energy. So the goal is to take this data, calculate up these values, and talk about what happens. Good luck.